So we end finally with talking about things that cause electrons to localize in solid state systems. It turns out that these have more effect in nanoscale systems than bulk systems. The simulations in this slide are of a process called Anderson localization. This quantity W over V represents the ratio of the spread in energies at sites on this two-dimensional plane shown here relative to the energy itself. So the larger this number W over V, the more disordered the system. Once again, W is a width, V is an absolute potential. So on the top, you see that at a ratio of disorder to absolute value of energy of about 5, there is a somewhat uniform distribution of electron density across the simulation. However, you see that when this ratio reaches 8, all of the electron density is now concentrated in the middle of this plane quite arbitrarily. This phenomenon in highly disordered systems has to do with multiple scattering. If the system is disordered enough, then one in general can always find a path for a scattered electron such that the backscattered electron returns along exactly the same path, with the result that a standing wave is formed. Now, this might sound highly improbable, but of course this is precisely the path that has the effect of creating a standing wave. Because of Anderson localization, one observes some quite unusual phenomenon, particularly in nanostructures of low dimensionality like wires. The effect of thermal energy, heat, is usually to increase the resistance of a material. A hot light bulb is very much more resistive than a cold tungsten filament. However, in nanowires that are disordered, one frequently observes a phenomenon in which the resistivity decreases with increasing temperature. And the reason for this is actually fairly easy to see. If the electron states are localized over some spread of energy, then transport, rather than being via block waves in the system, come via thermal hopping from state to state. And it's these upward jumps in energy that will dominate the overall transport, and hence transport will increase as temperature increases because of the Boltzmann factor. Another type of localization is very important, specifically in one-dimensional systems, and relevant to the whole issue of conducting polymers, of which more in Chapter 8. So supposing we have a one-dimensional tight binding type lattice with one electron per unit cell, and so that the dispersion looks as in this panel A here, this epsilon 0 minus 2 torr cosine Ka. Now remember, this system is half filled because it's one electron per unit cell. What Piles showed was that in systems like this, it's always possible to have a distortion in which every other atom moves. So here we make the unit cell A minus delta, and here A plus delta, and so on. What does this do? Well, it now means that you double the unit cell. It consists of two unit cells, the A plus minus per delta and the A minus delta. So this is the new unit cell, which has a length of 2A. So the Brillouin zone boundary, rather than occurring at pi over A as it did in the undistorted lattice, now occurs at pi over 2A. In consequence, a gap opens up at this new Brillouin zone boundary, So if we were to draw this out magnified, the cosine type dispersion will be evident at the boundary here. And so electronic states in the top branch are raised in energy, but the top branch is not occupied in this 1 electron per unit cell system. The lower branch has the electronic energy of electrons near this new zone boundary reduced by some amount delta. In order to achieve this, we had to put an elastic distortion into the system of an amount little delta, and this would take an energy a half the spring constant times little delta squared. As long as this is less than the lowering of electronic energy, a Piles distortion will occur, creating a filled band, a gap, and switching off conduction in a one-dimensional system.